We are surrounded by plastic. It's everywhere, from the moment we wake up to when we go to sleep. But have you ever really stopped to think about how it's made? In this explainer, we're going to peel back the layers on this material we see every day and find out how it goes from raw stuff in the earth to the finished product right in your hands.
It's a pretty wild question when you think about it, right? How does this black, sticky goo, crude oil, get transformed into something as perfectly clear as a water bottle or as precisely molded as a car dashboard? Well, the jury involves some serious heat, a lot of pressure, and some absolutely brilliant chemistry. So let's break it all down. Okay, so our journey starts deep underground. Now, there are a few exceptions, but the story for almost all plastic begins with fossil fuels. It's a massive industrial process that takes this raw material and completely transforms it. That's right. While you can make plastics from things like natural gas or even coal, the most common starting point by far is crude oil. And it's not just one single thing. It's this rich, complex soup of all different kinds of organic molecules, just waiting to be pulled apart and put back together in new ways. So how do we get from a liquid oil to a solid object? It's this really cool four-step process. First, you take the crude oil to a massive refinery where it gets heated up. This distillation process separates it into different groups or fractions. One of these, called naphtha, is the key ingredient we're looking for. Then that naphtha gets broken down even more into these tiny little molecules called monomers. The best way to think of them is like single Lego bricks. And finally, you get to the magic step, polymerization. Inside a reactor, all those individual Lego bricks, the monomers, are snapped together into these incredibly long repeating chains. And those chains, those are called polymers. That's the real essence of plastic. Okay, so once we've made those long polymer chains, the process hits a huge fork in the road. And this is really important because how those chains are structured and how they're bonded together creates two fundamentally different families of plastic, and each one has a completely unique personality. So on one side, you've got thermoplastics. With these, the long polymer chains are just kind of held together by weak bonds. Think of it like a big bowl of spaghetti. All the strands can slide past each other pretty easily. But then, on the other side, you have thermosets. Now, in this family, those chains are fused together by strong chemical crosslinks. They form this rigid, permanent net. So here's the key takeaway. One can be melted down and reformed over and over, and the other, it's a one-time deal. Once it's made for good. So let's dive into that first family, the thermoplastics. Honestly, the easiest way to think about them is to picture a bar of chocolate. You can melt it down, pour it into a mold, let it cool and get hard, and then you can do it all over again, as many times as you want. And that is the absolute key property of thermoplastics. They soften up when they get hot, and they get hard again when they cool down. And this whole process is totally reversible. This ability to be remelted and reshaped is exactly why this family of plastics can be recycled. The heat doesn't permanently wreck the molecular structure. And you know these materials really, really well, even if you don't recognize all the fancy names. PET, that's the clear plastic that makes your water bottle. PVC makes up all those sturdy pipes. Polypropylene, man, that's in everything from car bumpers to your food containers. And polycarbonate, that's what makes eyeglass lenses so incredibly tough. So what's the trade-off? I mean, the pros are huge. Thermoplastics can be recycled, they're highly resistant to impact, and they can have a really beautiful high-quality finish. But the big drawback is right there in the name. Thermo, which means heat. They get soft when they're heated, which makes them a pretty bad choice for anything that needs to handle high temperatures. All right, now for the other side of the family, the thermosets. If thermoplastics are like chocolate, then thermosets are like baking a cake. Once you mix the batter and you bake it, a chemical reaction happens. You can't unbake the cake, right? You can't turn it back into batter. It's a permanent change. See, thermosets usually start out as a liquid resin. Then you cure them, either with heat or some kind of chemical catalyst, and that's when those super strong, irreversible crosslinks form between the polymer chains. This locks everything into a rigid three-dimensional structure. And once it's set, it is set forever. You can't just melt it down and start over. So where do we see these guys in the real world? Well, you find them anywhere that durability and heat resistance are just non-negotiable. Polyurethane gives us the foam in our couches. Epoxy is that super strong glue that holds everything together. Silicone is used for durable sealants. You can see the pattern, right? They are made to endure. The benefits are pretty clear. Incredible resistance to heat and corrosion, amazing strength, and they hold their shape perfectly under stress. But All that strength comes at a cost. Because that chemical change is irreversible, you can't remelt them, you can't reshape them, and most importantly, you cannot recycle them. So if we only start with these two main families, how on earth do we get thousands of different kinds of plastics, each with its own unique properties? Well, the answer lies in the secret ingredients, additives. You can think of them as the spices we add to our plastic recipe. You can really get a sense of the sheer variety of these spices. We're talking about major categories like fillers, plasticizers, flame retardants, cross-linking agents. The list goes on and on. And these aren't just minor tweaks. We can toss in colorants to change the hue, UV stabilizers to protect it from the sun, or flame retardants to make it fire-resistant. Each one of these additives is like a special instruction that gives the base polymer a whole new superpower. Let me give you a perfect example. We can add fillers, things like talc or calcium carbonate, to a polymer to make it stronger and even cheaper to produce. Or we can add something called a plasticizer to a really rigid plastic like PVC. Now, without them, PVC is used to make hard pipes. But with them, that exact same base plastic becomes soft and flexible enough for things like insulating electrical wires or, get this, even baby pants. That's the power of additives. And the level of control here is it's incredible. I mean, just look at the classification for one single type of additive, fillers. You can see how it breaks down into major types like particulate and fibrous, and then into all these subtypes like reinforcing or non-reactive. This is the level of detail engineers get to work with. It really shows you that plastic isn't just one material. It's a whole universe of customized materials, each one precisely engineered for a very specific job. So that brings us right back to that great divide. On one hand, we've got thermoplastics, the ones we can melt down and recycle into new things. And on the other, we have thermosets, which are built to be incredibly durable and last, well, pretty much forever. It really leaves us with a final thought to chew on. In a world that's grappling with waste, which one is truly better? The one we can reuse or the one we never have to replace?